interference into UMTS space stations. A few words about the principle of UMTS that is important when we do interference investigation to understand. In UMTS, each bit is coded with a binary key before it's modulated. And due to that, the spectrum widens by the number of bits or chips in the code. But the advantage of this is that multiple users can transmit on the same frequency at the same time. This is what we call CDMA, Code Division Multiple Access. And the receiver can separate the different users by doing a comparison between the received bit stream and the known binary codes. And another advantage is that we gain immunity against interference by the so-called system gain. And we can understand that on the second sheet when we look at the principle of CDMA. The transmitter side gets, in this example, 4 bits that we want to transmit. This is what we call slow user data. It's relatively too slow compared to what we are going to transmit. And this slow data will result in a narrow bandwidth. But instead of the user data, we add or we code these 4 bits with, in this case, a 4-digit code. And instead of the user data, we transmit 20 bits. Instead of 4, we transmit 20 bits, which consist of the code itself and the negated code, depending on whether we have 1 or 0 to transmit. Of course, since we have to transmit 4 times more bits in the same time, we get 4 times wider spectrum. So this coding will result in a wide spectrum. But the energy of this is the green area here is the same in both cases. It's only spread over a wider bandwidth. So far, it does not look very logical that this increases the immunity against interference. But this becomes clear when we look at the receiver side. We receive the wide spectrum with the 20 bits, and that is again decoded by applying the same process as on the transmitter. So each bit is added. Actually, it's an exclusive OR operation that is performed, and the results will be 4 zeros or 4 ones, depending on the user data. Now, this data is only changing slowly, because every 4 bits are equal. So we can pass this through a low-pass filter, and we integrate that. And that will eventually give us our slow user data with a narrow spectrum back again. So we reduce the energy in the wide spectrum again to be narrow. Now, if we have interferers in that, this is actually the system gain that we were talking about before. If we have an interferer, it can be wideband or narrowband. If a wideband interferer is present, that adds to the wideband spectrum. And it will also result in fast data here when we decode it. But this fast data does not fit to this key. So if we perform on other bits, here on random bits, this operation, we get also fast changing result. And that fast changing result will not pass through this filter and will be low in amplitude after filtering. So that does not really harm very much. And the same is with a narrowband interferer. The narrowband interferer will result in the 20 bits here all being 1 or all being 0, depending on which end the decoder is affected. Now, if we had 20 ones or 20 zeros here, and we do this operation, we again get fast changing data as a result. So even if we have narrowband interference, it will result in a fast changed data stream, and that will again be suppressed by the integration and also not come out. So the user receiver is actually not so much affected by the interference unless it is as high as the system gain. But if we look at it from the monitoring side, we see that spectrum with the spectrum analyzer. The spectrum analyzer does not perform this decoding. So this is what we see. And the advantage of the system gain means that we have a wideband spectrum that can be seen to the left or to the right, or both ends of the user spectrum, or if it's a narrowband interferer, it has to stick out of the users, of the normal use signal, unless it is, if it does not stick out of the spectrum, we have no interference. So that makes life a bit easier for us when we want to investigate it. It must clearly be seen on the spectrum analyzer to be really harmful. But there are some restrictions to this principle, and one is that the separation of the signals from multiple mobiles for the base station works only if all of them are received with the same level. And that means that the base station has to constantly tell the mobile on how much transmitter power it has to use. And if the base station is interfered, it just asks all mobiles to raise power to overcome the interference. But of course, for faraway mobile, they are already on maximum power. They have to be dropped because they cannot increase power further. So that means that if we have interference to the operator, the effect is that the coverage of the base station decreases. We cannot serve the faraway mobiles anymore. And another thing is that mostly all stations of one network operate on the same frequency. So there is no frequency changing possible, which means that one interferer can disable a whole base station. So that may be quite severe. The operator can recognize an interference because modern UMTS stations measure the unwanted level in the code domain, and they return an indicator called RTWP, which is received total wideband power. And that sort of display can be produced by the software of the operator. This is an example of a UMTS station where from this moment on the sector 1, the sector 2 and the sector 3 is interfered. Sector 1 is nearly not interfered. So sector 2 is most interfered, sector 3 is less interfered. So if we work on that interference, the steps are, we first have to see how we can recognize the interference. And as I already said, we must see the interference signal on the spectrum analyzer. If we don't see anything on the analyzer other than the user signals, we cannot have harmful interference. When the uplink channel is viewed with a spectrum analyzer, as I said, wideband interference should be visible to the left and the right of the used channel, and narrowband interference must stick out of the wanted signal. So this is a display, this is a spectrum recording we got from the operator. You can see the wanted signal here. This is the 5 megahertz wanted channel, and this is a narrowband interferer that sits on that channel. So when we investigate this interference, first we look at the map. We have here this interfered station with the 3 sectors, and we saw from the previous sheet that this sector was most affected, this sector was a bit affected, and this sector was not affected. So we can assume that the interferer is somewhere in this angle range. So what we do is we position our measurement car somewhere here, near the base station, in the range of the expected interferer, and we try to pick up the interferer in the car. If we can pick it up, no problem, we just follow the bearing, do whatever we do on normal interferers to locate it. But in many cases, we will not be able to see the interferer in the car because the antenna is much higher and more sensitive than we have in the car. So in that case, we need to do a measurement on the UMTS antenna. And the point where we measure is the antenna port. Usually the UMTS antennas are cross-polarized, and usually we have two antenna lines coming down from each of the sector antennas, working on two different TX-RX units of the UMTS station. And we can use one of these antenna lines to connect our analyzer. And it is also very important that we do the measurement with a bandpass filter that passes only the uplink, because we need to suppress the downlink of this and other UMTS base stations. Otherwise, we get overloading in our analyzer and we see signals that are not there. So it's absolutely important that we have a bandpass filter there. Without that, we don't even consider this measurement. Now, the advantage of this setting is that we can leave one of the RX-TX units connected to half of the antenna while we do the measurement on the other half of the antenna. And it is very important that we can do the measurement while the UMTS station is still running. Most people think it's better to shut down the station and then connect our equipment. But the problem, what happens then is that if we have a weak interferer and the UMTS station is not running, is shut down while we do the measurement, then the mobiles that are nearby will cover the interferer because their levels are too high. If we look at the map, we have the interfered station here, and we have neighboring stations there and there. So if we have a mobile that is close to our interfered station and using UMTS, normally it is served by our interfered station, and that station tells the mobile to reduce power because it's very close. But if we shut down the interference station to do the measurement, then the mobile seeks for the neighbor channels, for the neighbor cells. And then it is served by another cell, but that is far away. So the mobile has to increase power in order to reach that faraway station. And this increased power will be seen when we do the measurement here. So it will actually it may cover our interferer. That's why it's important to keep the station running while we do the measurement, and that is possible. You will get an error message when you start up the station, but it can be ignored, so it can work on one of the antenna parts and while we do the measurement on the other. So most common interference sources is DECT telephones. We have US imported DECT telephones because in the US the DECT frequency band reaches into our UMTS uplink band, and if the DECT telephones from the US use the upper channels, they are in our band. And we also have faulty DECT parts. Some DECT telephones develop the fault that they jump to the UMTS band when they get faulty. The user does not notice it, only that the station is not working anymore, the DECT station, but it may still serve as a charger for the mobile. We can identify this type of interference, although the spectrum in case of a faulty DECT telephone is not like DECT. So this is a typical spectrum that we recorded, and you cannot recognize it from the spectrum as a DECT phone. You can only see it's a pulsed signal. But if you go to the time domain in zero span, you can see the 10 milliseconds pulse repetition, and you can see pulse lengths of less than 100 microsecond. This is quite typical. If you see that, you can already know that the interferer is a DECT station. Another common interference source is antenna amplifiers. The high amplification of active antennas sometimes lead to a feedback from the output to the input. So they can radiate, and that can go into the UMTS band. Mostly these are unmodulated carriers, but if we put an AM demodulation, you can usually hear 50 or 100 hertz humming. They are often not stable in frequency, so this is a recording of such a thing in max hold. You can see that the antenna amplifier sweeps starting from here and sweeping across that whole frequency range. But it's not a pulsed signal, it's a continuous signal. And the second common interference source that we found is sideband emissions from alarm routers operating in 2.4 gigahertz band with insufficient suppression of the sideband emissions. We can identify them also in zero span. We have different pulse lengths depending on the traffic on that alarm router, but we have very larger pulse repetition rates, about 100 milliseconds. The spectrum is indifferent, but the pulse repetition rate is much longer than for DECT. So we don't see the 10 milliseconds, we see something in the range of 100 milliseconds. And that is an indicator for such a sideband emission. So at least with these informations, we know already something about the sources that we're searching. Okay, that was, I think, 20 minutes, very fast, I agree, but and there should be much more to say about this topic, but given the time, I think that should be it. Thanks very much.